All right, let's get started with lecture 2. So today we're going to basically talk about matter waves for electrons or for other things that were considered as particles. We will introduce the concept of the wave function and talk about what information it contains. And discuss the probabilistic nature of quantum mechanics in the simplest kind of possible terms. So last time the main thing we did last time was describing the photoelectric effect. And basically what it was an experiment where you shine light on a piece of metal and it emits electrons, and then there was a clever way to experimentally measure the kinetic energy of the individual electrons that are emitted from this piece of metal. And the experimental observation was that this kinetic energy is independent of the intensity of light that you shine on this piece of material, but it has a linear dependence on the frequency of light. And frequency is basically the color. So that's kind of a contradiction with classical physics. Basically, if you treat light as an electromagnetic wave, you expect that the higher intensity to correspond to larger electric fields, and then when they couple to electrons inside this material, they exert larger forces, and they should give a larger kinetic energy when they manage to kick them out of the material. And it should not really depend, according to the classical theory, on the frequency of light. But this experimental observation kind of contradicts this picture. So Einstein came with this bold theory that, well, let's treat light as a bunch of particles, as packets of energy, and let's assume that the energy they carry is proportional to the frequency. So this explains the photoelectric effect, and then you can say, well, here's really a correspondence between a particle-like thing, the energy of a packet, and a wave-like quantity, the frequency. And de Broglie managed to kind of make use of other properties of light, basically thinking of light as massless relativistic particles, managed to show that there's another relationship. Basically, the momentum is h over lambda, the wavelength. Again, the momentum, a particle-like quantity, is inversely proportional to the wavelength, a wave-like feature. Of course, energy and momentum, I mean, waves do carry energy and momentum, and you can talk about energy density, for example, in a wave, or the energy flux, etc. So those are, a bit more general than particles. But if you want to describe particles, you would talk about their energy and momentum. And it seems that there's some wave-like nature, at least for light, where the frequency and the wavelength, the salient kind of characteristics of a wave, are related to the energy and momentum they manifest in their particle-like behavior. So that was the upshot of the last lecture, and the conjecture was that, well, maybe particles like electrons, there's something wave-like about them, and maybe there's some associated frequency and wavelength, and maybe it has some manifestation in the physical reality. So you're familiar with the double-slit experiment, like interference experiment for light. You shine light on two slits, double for light, So suppose you have two apertures, two holes, and there's a screen here that can be illuminated, let's say by some light that you shine on this screen that has, or on this barrier that has two openings. And treating light as electromagnetic waves, you know that, well, there's going to be in different places on the screen, there's like a wave that starts from this hole and reaches that. Then there's a wave with the same frequency and wavelength that starts from this point and reaches any point on the screen, but they travel different lengths, so they have different phases when they reach the screen. And then the electric field for one will be like cosine, will be the amplitude times the cosine of one phase, and the electric field for the other one is the amplitude times the cosine of another phase. And depending on whether these phases are the same or differ, for example, by 2 pi, you get constructive interference. And if they're out of phase, that they differ by pi or some odd integer multiple of pi, they have destructive interference, so you get a dark spot. So we did all of that when we were studying wave optics, treating light as an electromagnetic waves, and we're familiar with these patterns that emerge there. There's going to be like a bright central fringe, and then other kind of bright fringes and some dark fringes, etc. So that's what happens for waves. Like light definitely does it. Water waves would do similar things. Now, if you have particles, let's say you have a bunch of rocks, right, or baseballs that you just throw at a wall with two holes in it, and then there's another wall behind it, and it's kind of sticky, so when these particles go through the first screen, they reach the wall behind it and they just stick there. Well, what are we going to see? So first, suppose, let's think about particles doing a similar game, or playing a similar game for particles. And let's say we have one opening, right? So imagine you're here and you have these particles and you throw them toward an opening in a wall. So some of them will go through, some of them will hit the wall and kind of get stuck there, don't go through. And then behind it, there's some screen. So if this particle goes through, if this piece of rock goes through, it's going to hit somewhere on the screen. And let's say we put some really strong glue there, so it's going to stick there. Or maybe the particle is so energetic that it's going to like punch a hole there. So there's going to be some evidence that the particle hit somewhere, right? The particle is just a localized chunk of matter. So we can detect it somehow. Well, if you have one hole, what are we going to see? Well, suppose, these particles keep hitting and they accumulate there. So if you now think about the intensity, like how many particles hit a particular area, well, most of them will kind of go through the center, so we're going to see something uniform near the center, and then as you move away, there are fewer and fewer particles because they were blocked by the wall, so this kind of decays, and you're going to see something like this. Let's say density of particles, right? The number of particles, let's say per unit, per unit area, surface area of that wall. Okay, we're going to see something like this. Quite natural, right? What you would expect if you do that. Now, what happens if you have two holes? Well, so let's say that's the first one. This is the second one. And this is the screen. And again, you're throwing rocks at this wall. Well, a particle that goes through, some of the particles will go through this hole, some of them will go through the other hole, right? So, and they couldn't care less about like what happened before or after, right? If a particle is going through this hole, it doesn't care how many particles went through the other hole, right? They're completely independent things, right? You can throw them one by one and each of them goes either through the top hole or through the bottom. So it's going to hit the screen somewhere. So basically the pattern that we'll see is going to be the sum of these two, right? We're going to get something like this from this opening, something like this from this opening, and then, you know, that's the number of particles which are stuck on the wall. So we're going to see something that, you know, roughly, maybe there's a little dip here. Then it's basically like this is almost roughly twice this density. So let me redraw that to reflect that fact. Okay, so we go here, yeah, roughly something like this. And then it goes down here, goes down here. So roughly the sum of these two, that's just a number of particles. If you look at them, you're going to see something that's uniform. Maybe, depending on how far these are, maybe there's a slight dip in the middle, but basically, like, you're not going to see fringes, right? That's what you expect with stuff that behave like particles, stuff that hit the wall one by one, are detected as one point on the wall. All right. So now I want to show you a remarkable experiment. I mean, historically there have been experiments where, in the olden days, where this behavior, of course, could be inferred. But there's a recent experiment in the 21st century. I think it was done by the Hitachi Corporation. It was done in industry when they were making these CRT televisions. They had some technology, and you know they did this experiment. So basically it's the same setup. You have two slits, but you shoot electrons instead of rocks. Okay, and they're gonna hit some screen. They somehow get detected. So when they hit, you know, there's some interaction, and you see a bright spot where an electron hits. And they have a very low intensity of electrons. So definitely they reach the screen one by one. All right. So let's see what happens.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biboson, thus creating a uniform distribution.
Right, so they seem to be detected like particles. They hit the screen one by one. So if they're behaving similar to rocks, roughly we should get a uniform distribution, right? Maybe there's a little bit of a dip at the very middle if there's some distance between the two holes. But basically we don't expect fringes. So let's see what appears in this pattern.
Without any interference when accumulated. Under such condition do electrons form a uniform distribution. But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
All right, so that's a remarkable experiment, right? So there's something behaving like a wave for these particles that very much look particles. They hit the screen one by one, like chunks of energy. So what is happening? How can we make sense of it? But then there's also something quite remarkable, right? Because where these fringes occur is an experimental fact. It's an observed quantity, like the distances between these. And we know that for light, that distance between fringes is determined by the wavelength. So if we know the momentum of these electrons, we know that the Broglie wavelength, it would be quite remarkable that this wavelength was what's determining that interference pattern. And that's exactly what happens. So quantitatively, if you measure the momentum of your electrons, and if you know the distances between holes, you know the distance between the holes and the screen, you measure the distance between various fringes, it agrees with just the theory of wave interference. For a wave that has a wavelength lambda equal to h over p, where p is the momentum. So that's quite a remarkable wave-particle duality. And then we want to try to make sense of it. So let's think through this. So what is happening? Definitely the particles are being detected one by one as particles. But there should be some mathematical object, right, that has a superposition in it. The way we got these interference fringes for light or for waves is that, well, if you want to write, let's say, the electric field at this point, it's a sum of an electric field for a wave emanating from this opening and an electric field for a wave emanating from the other opening. It's a sum of two things. Each of them has a phase in it, and that gives rise to those fringes. And this intensity that we observe is like the field squared, right? Remember, intensity of light so there's an electric field, right, at every point on the screen that you can think of E1 plus E2. So there's like E1 here, there's E2 there, and they add up. There's a superposition principle. The total electric field for every point is the sum of these two. And what we observe, this intensity, is the total field squared. So the intensity we observe for electrons, so if you have, let's say, these electrons being shot at a barrier with two holes, and we observe these patterns in the, basically what emerges. You have all these points, and ultimately you will see something like this. You'll see bright fringes and dark fringes. This is kind of like something squared, if you want to make an analogy, right? This is a density of electrons, which is somehow similar to the intensity of the electromagnetic field. So what is that something? Well, we don't know, but mathematically we can imagine there's some object that behaves like a wave, and when you square it, you end up with this pattern, with this density pattern. So we expect some mathematical quantity, let's call it psi, it's a Greek letter, to be a superposition for, let's say, hole 1 and hole 2, such that psi squared. So I'm going to take the absolute value because it turns out that psi will be a complex number, as I'll discuss in a second, gives us the density on the screen. Now, if psi squared gives us a density, there's also another interpretation. Like each electron is hitting somewhere. You look at it for a short time before those fringes appear, it looks like a very random process. Like they're hitting all over the place. So, but if, the brighter regions have a higher probability for the electron to be detected, then you're going to get, at the end of the day, when many electrons are detected, you're going to see a higher density of electrons there. Right? So more electrons hit in this region where you have like a bright fringe. So if there's some underlying probability to this random behavior of electrons, well, you have a higher probability of hitting the screen when you're in this region where there's a bright fringe than here when there's a dark fringe. So that's the probabilistic nature of quantum mechanics, largely due to Max Born. We talked about psi squared gives us the probability in this random process of detecting a particle. So we don't really know what this quantity is, but we call it the wave function because there's some wave involved somewhere. So psi is called the wave function. And then we have to get a little bit more quantitative here, right? Because on the screen, like there's some surface area, right? So what we're really talking about is the probability density. Because if you take a point on the screen that the surface area is 0, well, there's 0 probability that the particle hits there, right? You need some area for these particles to accumulate. So for simplicity, let's start with one dimension. With one space dimension. So if you think about particles hitting on a one-dimensional line, and then you have a wave function as a function of position x on this line, then for every point the probability is always 0 because there's no length there. But if you pick, let's say, at position x, you pick a tiny region of length dx, then we're saying psi of x squared times dx times that length is the probability of detecting the particle let's say between x and x plus dx in the limit of tiny dx, dx going to 0. So psi squared itself is called the probability density. And then, if you're in 2 dimensions, well, you can have a wave function that's a function of x and y, and then psi xy squared times the surface area in 2 dimension is again the probability. So again, to be clear here, let's say this two-dimensional space. You can label points by kind of their x and y coordinates. And then we're looking at position x and y, we're looking at a tiny square of surface area dx times dy. So this length is dx, that's dy. All right. So before proceeding, I briefly mentioned that psi is a complex number, and I know many of you may not be familiar with complex numbers. So I want to just take a few minutes. So let's do an aside. So to talk about complex numbers. So there are different ways to think about them, but basically one can define complex number as like a collection of 2 numbers, 2 real numbers. One is called the real part, another is called the imaginary part. So z, you can always think of x plus I times y. And x is the real part of z. Y is the imaginary part of z. And at this point, I mean, this is a notation. I could have maybe just used x and y like a pair and call the first one real part, the second one imaginary part. But if we want to connect these to real numbers, it's useful to define I as a quantity such that I squared is minus 1. So I is kind of defined as the square root of minus 1 in some sense. It's something that when you square it, you get minus 1. So for example, if I have z1 is x1 plus I y1, z2 is x2 plus I y2, then z1 times z2, this product becomes, you can just use kind of the standard rules of algebra. You'll get x1, x2 plus I y1, I y2 plus I y1 x2 plus x2 I y2. So this becomes x1, x2, I times I is minus 1, minus y1, y2, plus I factor out the I here, and I get x2, y1 plus, oops, this one is x1 here, x1, I, y2, plus x1, y2. Okay, so then one can say that the real part of z1, z2 is this, imaginary part is this. So you multiply 2 complex numbers. With this recipe, you're going to get a complex number. You add or subtract 2 complex numbers. Again, you're going to get a complex number. Okay, so there's something called the complex conjugation. So again, if z is x plus I, y, again, it has a real part and an imaginary part, then we define complex conjugate of z is called z star, or is denoted by z star, and is equal to x minus iy. So basically the complex conjugate of any real number is itself, and the complex conjugate of I is minus I. You just change the sign of I when you take the complex conjugate. And then the absolute value squared of a complex number is defined as z times z star. So that becomes, let's do this. So remember, a plus b times a minus b is a squared minus b squared. So this becomes x squared minus iy squared. So I squared is minus 1, kills that minus sign. It becomes x squared plus y squared. So this is always a real non-negative number. Sometimes it's helpful to have like a geometric representation. So think about the complex plane and different points kind of map to different complex numbers. So then, let's say this is the x, this is y, right? For each point you can imagine a complex number x plus iy. And then, then the associated z squared is this length, this radius, from the origin to that point squared. Right? From the Pythagorean theorem, that's just x squared plus y squared. Okay. So far we're just introducing some mathematical objects. So complex numbers are, basically you can think of them as a collection of two real numbers with some rules for addition and multiplication, etc. And all of those rules are summarized in saying I squared is minus 1, and then you write the complex number as its real part plus its imaginary part. And then just use the standard rules of algebra. So there is a very important identity known as the Euler Formula, one of many Euler formulas, which says e exponential of I times theta, right, is given by cosine theta plus I sine theta. So I won't go through the proof or motivation of this, but basically, like for those who are familiar with the Taylor expansion, for example, you can consider the Taylor expansion of an exponential, and all powers of I that are even become 1 or minus 1. The odd powers become I or minus I. And then you can Taylor expand both sides, collect the terms with an I, they give you the Taylor expansion of the sine. Collect the terms without an I, they give you the Taylor expansion of the cosine. But let's just take this as an extremely useful formula. Okay? So this gives kind of another way to represent any complex number. We can always write it as, let's say, rho times e to the I phi, right, where rho is just the square root of x squared. So let's say this is x plus iy. X squared plus y squared, that's like the length. So when you square it, you get the absolute value of z squared, right? In order to verify this, for example, you can imagine what happens to z star. Well, it's going to be rho times e to the minus I phi. The only thing we do is change the I to minus I, and then if I multiply these, of course, e to the I phi and e to the minus I phi they give me 1, right? It's e to the 0. The exponents cancel out, so z times z star is rho squared. And rho squared is, of course, x squared plus y squared. And there are some trig identities. So for example, x is going to be rho cosine phi, and y is going to be rho sine phi. So the geometric picture on the complex plane, again, if this is x, this is y, that's the point that we associate this complex number to, is really like this way, right? And this x plus I, y is thinking in terms of Cartesian representation. This way is thinking about a polar coordinate. So this length from here to here is rho, and this angle here is phi. Right, so again, to think about these now, see, if I look at this triangle here, right, this angle is phi, x is adjacent to phi, rho is the hypotenuse, so x over rho is going to be cosine phi, and that's, you multiply both sides by rho, you have this equation. And similarly, this length from here to here is y, so y over rho is sine phi, right? Y is opposite the angle. All right, so that was just an introduction to, a very quick introduction to complex numbers. And it turns out in quantum mechanics, we are forced to have wave functions that are complex. Basically, the key differential equation that governs the dynamics or the time dependence of this wave function psi ends up with an I in it. So it can make the wave function complex, basically. So if there is an I in an equation that governs the dynamics of a quantity, even if you start, let's say, with a real wave function, as it evolves, it becomes, it's bound to become complex, right? That I ends up somewhere in the solution of the differential equation. All right. So let's do maybe one quick example. So I want to focus on quantum mechanics in 1 dimensions. Okay. So let's say we have a particle described by a certain wave function. So example. So let's say consider a particle with wave function, let's say psi of x, particle in 1D, in 1 dimension, which is, let's say, equal to just some constant a for x between 0 and some length small a, and is 0 otherwise. Okay, so first, let's say, determine a. What should that value be? So again, what is the wave function? So the interpretation is that psi of x squared times the x is probability of finding the particle in x, or yeah, in the interval x and x plus dx. Right, so if that's the x-axis, if the wave function is 0 outside this range, let's say this is 0, this is a, So here the wave function is 0, so wave function squared is 0. So if you pick any tiny interval anywhere here, the probability of finding the particle there is 0. Here, let me plot psi squared. I'm putting the absolute value because it's kind of good practice, but this is, let's say a is a real number, so this is just psi squared. So psi squared is going to look like, basically like square, where this height here is a squared. Okay. So what does it mean? It means that basically any interval of length dx you pick between 0 and a, the probability of finding the particle in that interval is going to be a squared, a constant, times dx, right? So, but the particle exists, right? So the probability that it's somewhere is 1. So if you add the probabilities for all the intervals from -infinity to infinity, it should give us 1, right? So that means basically I should write the integral from -infinity to infinity. I'm summing over all these tiny probabilities times dx. That's a tiny probability for one interval at position x. It must be 1. Now this quantity, the integrand, is 0 outside this range, so for this particular problem it implies that the integral from 0 to small a of wave function squared, which is capital A squared dx, is 1. I factor out the a squared because it's a constant, so integral from 0 to a of dx is just a. So that means a squared is 1 over a, and capital A becomes 1 over square root a. So we found like the normalization constant in front of a wave function that's constant in some interval and is 0 outside. And of course you can have like more complicated situations. So if I now ask you, what is the probability that you find this particle, I don't know, in x larger than a over 3? So what is the probability of finding the particle at x larger than a over 3? Well, so let's draw this again. So we put my 0 here now. This is a. A over 3 is going to be here. So the probability of being larger than a over 3 is like being in this region, right? So again, you can consider all the tiny intervals in this region of interest and add those probabilities. When you're above a, that probability is 0. So this probability ends up being integral from a over 3 to a, right? Because psi squared is 0 for x larger than a, of psi squared, which is just capital A squared. And capital A squared is 1 over a. And this becomes clearly, you can factor out this, and the integral gives us 2/3 of a, so this becomes 2/3. And that's quite expected, right? We have a uniform probability. Basically, all these tiny intervals have the same probability, so this length is like 2/3. So that's the probability of the particle being found there. So experimentally, what does it mean? So imagine you have like 10 million particles, identical particles, each having the same wave function, having this wave function to begin with, right? This guy. So I just have some kind of a detector that finds the particle, and it's going to be a random process. Every time I'm going to find the particle somewhere, right? And every time, like, I can make a huge list of the positions I found the particles. Yeah, so suppose in that list, you know, So large list, x1, x2, x3, up to x, I don't know, 10 million, right? Okay, so every time I can go through that list and look at each one of them, and I check, is that number larger than a over 3 or smaller than a over 3? If it's larger than a over 3, I put a cross here, or the dot here. If it's not, I don't. So some of them will get a dot because they're larger than a over 3, some of them won't. And when I repeated this experiment over and over many times, I'm just going to divide the number of observations where the position, this random thing that I measured, was larger than over 3, and just divide it by the total number of measurements, in this case 10 to the 7, and in the limit of many measurements, that should go to 2/3. Okay, so that's the interpretation. Let's do another example, again something very similar with a slightly more complicated wave function. So imagine, let's say psi of x, again in 1D, is given by, let's say it's equal to, so I want something that looks like this. Let's say this is psi, maybe like a triangle. Let's start from 0, goes up to some value, comes down. So if this is a over 2, this is a, this is 0, so it's going to be some number, right? It's going up with some slope times x, let's say for x between 0 and a over 2. And then it reaches, so this value here should be a times a over 2, right? If that's the form. Then it's coming down from that height, so it's going to be a times a over 2 minus x, right? It's a line of kind of the minus that slope, so the slope should be minus a, and at x equal a over 2, actually it should be here, I should have a, right? So when x is equal to, when x is equal to a over 2, I get a times a over 2, which is this height. And when x is equal to a, which is this point, it goes to 0. So that's good. So that's valid for, let's say, x between a over 2 and a. And don't worry about equal sign. I mean, 1 point, the probability of being at 1 point is always 0. So you can, if you want to be careful, you can always make, for example, one of them less than or equal to. And then it's 0 otherwise. So when x is smaller than 0, a negative number, or when it's larger than this small a, we get 0. So that's a more complicated wave function. It has 2 linear pieces. And let's say we want to find capital A, right, the normalization constant, in terms of small a, that length. Okay, so how are we going to do this? Well, again, the general condition is that integral from minus infinity to infinity, right, of psi squared dx must be 1. Okay, so this, it's 0 outside this range. So this gives me integral from 0 to a over 2 of a squared x squared dx, right? Integral from here to here of this wave function, of the wave function in that region, plus integral from a over 2 to a of a squared a minus x quantity squared dx, right? The wave function in this region squared. This sum must be 1. And that's something that will determine the normalization constant for me. So I can do these integrals and find it. And then if I want to find the probability of, the particle, of finding the particle in some particular region, I just need to calculate the integral in that region of psi squared, right? I'm summing over these tiny probabilities for these narrow slivers of length dx within that region. All right, so let's push through this calculation. Let's see what we're going to get. So I believe this like becomes a squared integral from 0 to a over 2 of x squared dx, just this term, which is x cubed over 3, so it's going to be a squared x cubed over 3 running from 0 to a over 2, so it becomes a squared a cubed over 24, I believe. Right, so that's a simple integral that we do, right? A over 2 squared is a squared over 2, a over 2 cubed is a cubed over 2 cubed, which is 8, and 8 times 3 is 24. The other integral, we can do it, we'll kind of expand this or make a change of variable or something, but it's basically clear that, you know, if you look at psi squared, this should go up kind of quadratically up to its maximum value, and then basically like this is like there's a symmetry axis, so this is going to be the mirror image of that, so it's going to come down in the same way, right? So if you think about the area under this curve, it should be the same as the area under this curve. So therefore this whole integral is just twice that, so I should get a squared a cubed over 12 is 1, and that gives me a is the square root of 12 over a cubed. To do this integral, I mean, we can do it. So one way to actually see that symmetry, maybe algebraically, is to say a minus x is z or something. Or let me use a Greek letter so we don't confuse it with complex numbers. We call them z. So I'm just making a change of variable here. Let's call that beta. So then dx is minus d beta, and then when x goes from a over 2 to a minus x goes from a over 2, right? A minus a over 2 is a over 2, to 0. A minus a is 0. So it's going to give me integral from a over 2 to 0 of a squared beta squared minus d beta. That's the dx. So that's just minus integral from a over 2 to 0, which is plus integral from 0 to a over 2. So by this change of variable, we see it's exactly the same thing as the first term that we just calculated. All right, I think this is a good place to stop. So today we went through the double slit experiment, and we to some extent motivated the probabilistic description of quantum mechanics in terms of a quantity known as the wave function, which when you square it, when you take the absolute value squared, gives you the probability density. And we had some practice in one dimension thinking about the normalization of this wave function and calculating the probabilities of finding the particle in some particular region.